Hey everyone, welcome to the EmSAT Physics tutorial videos. So what we're going to do is the same thing we've been doing with math. We're going to solve some questions from the specimen paper. I'm going to give you the explanation on the topic, the formulas to use, and the best way to solve it. So let's get started. This question says, 4 forces are acting upon a block on a horizontal surface. As a result of these forces, which of the following is true? And they gave us some answers basically about the motion of this block. So it's about Newton's laws of motion, specifically the first law of motion. And instead of boring you to death while watching me write it, here it is. Bam! So it says, a body at rest will remain at rest, and a body in motion will remain in constant uniform motion unless acted on by an unbalancing force. Let's see what that means. Imagine I have a box over here. Here's my famous box. And let's say there's a force pushing it to the right with 10 newtons. So because this force is all alone, we would say this force is unbalanced. There's no other force to balance it out. So if you have just one force, what I can tell you is this box will accelerate to the right. And now let's take another box over here. Same thing, it's a box, it's on the ground. Now this one, let's say there's 10 newtons to the right, but also there's 10 newtons to the left. And then I would ask you, is this box going to move or not? I'll give you a second to think about it. Now most of you will say, well no, there's 10 newtons to the right and 10 newtons to the left, and that means, the forces cancel out, right? They're balanced, and so it will not move. But that is not necessarily true, okay? The correct answer is, if it was at rest, it will remain at rest. But if it was already moving, then it will continue moving in constant uniform motion. That means if it was already moving, which I don't know right now, in my example, we don't know, right? But if it was already moving, it would continue moving at the same speed and same direction. And if it was not moving, then it would remain not moving. It would remain at rest. So having forces balanced like this, canceling each other out, if you will, does not mean there is no motion. It only means there is no acceleration. Okay? So let me repeat that for the crowd in the back. Balanced forces, balanced net force means acceleration is 0. Unbalanced means there is an acceleration in the direction of the resultant force. Just to seal the deal here, let me give you a third box. Let's imagine I have somebody pushing with 7 newtons this way and 10 newtons that way. Well, these are vectors, right? So I can simplify this diagram, because there will be a resultant force of 3 newtons to the left. That's how vectors work. So this box will accelerate to the left because the resultant force is to the left and it is unbalanced. Now, does this box move to the left? We don't know. Just because you're accelerating to the left does not mean you are moving to the left. The only indicator of direction is velocity. And we'll touch on that a little bit later. In the case of this box, let's go back to the box. We can tell that the vertical forces are balanced, and therefore there is no acceleration in the up or down direction. Now, what about left and right? I can see that there is 120 newtons to the left and only 100 to the right. So the net resultant force is 20 newtons to the left. Because this is an unbalanced force, we will have an acceleration in the same direction as a resultant force, making our correct answer, the block accelerates to the left. Okay, this question says a 2 kilogram mass moving with a speed of 3 meters per second to the right collides with a 7 kilogram mass that is moving to the left with a speed of 2 meters per second. After collision, the 2 kilogram mass was moving with a speed of 2 meters per second to the left. And what is the change in momentum of the 7 kilogram mass? So this question is about momentum, and more specifically conservation of momentum. I'm going to draw out this scenario because I always think it's really useful to draw when you're doing physics. Here's the 2 kilogram mass. It's going to the right at 3 meters per second, and it's going to collide with a larger mass, there you are, of 7 kilograms. And this one is moving to the left at 2 meters per second. Now these two are going to collide, crash, bing, boom. And then we know that this 2 kilogram mass, the smaller one, the 2 kilogram mass, is going to move to the left at 2 meters per second. Whereas this larger 7 kilogram mass, well, that one we do not know what its velocity is going to be like. So in conservation of momentum, this is the rule. the total initial momentum before collision is going to be equal to the total momentum after collision. That means I'm going to add up momentum of object 1 before the collision, momentum of object 2 before the collision, and this is going to give me the exact same thing if I add momentum of object 1 after and momentum of object 2 after the collision. Now momentum is simply the multiplication between the mass and the velocity of this object. So object 1 before, and here is object 2 before. Then you have object 1 after and object 2 after. So most of these we have, let's go plug them in. So M will be, well, let me use that light blue that I like. So M1, object 1 will be 2. V will be 3. And here's a little something. M2 will be 7. Now be careful with this velocity. You'll notice that it's in opposite direction of this one. So if I place this one as positive, then I've declared that anything to the right is going to be positive. And by that logic, then anything going to the left must be negative. You have to find a sign convention and stick to it throughout. Okay? It doesn't make sense to put this one as positive 3 and this one as positive 2. They're in opposite directions. They must have opposite signs when you're doing your calculations. So let's look at the after collision scenario. When you have M1, that's 2, its velocity again to the left. So I'm going to make it negative 2. Now this mass is 7 still, but we don't know this final velocity of object number 2. So using our algebra, we can figure this out, right? This is 6, this is minus 14. Here we have minus 4 plus 7 V2F. I bring the 4 over to the left. This is not math, but you guys probably know this already. And then you get minus 4 equals 7 V2F. And if I divide both sides by 7, then I have my final velocity V2F is minus 4 over 7 meters per second. Now minus, because I said plus is to the right, that means minus, this one's going to be moving to the left. Okay? Now the question does not quite ask me what is the velocity of this second object. It says what is the change in momentum of this 7 kilogram mass. So if we go to change in momentum, like we said, momentum is simply mass times velocity. So change in momentum is just the mass times the change in velocity. And change in velocity is always the same, right? Change in anything, whenever you see delta something, it's always final minus initial. And so I'll plug some numbers in here again. The mass is 7. We know it's 7 kilograms. Its final velocity is minus 4 over 7. And its initial velocity is negative 2. So if I plug all of these in, I get 10 kilogram meters per second. Now the sign is important because positive means to the right, and you'll notice that this object, this 7 kilogram object, was going at 2 and then it slowed down. It's only going about 0.57. What that means is the change in momentum is towards the right, which suits with my sign convention, and that's why this one is positive, making the correct answer D. Now, full disclosure, there was an easier way to solve this problem, okay? But I wanted to take this as an opportunity to teach you guys about this, how to work these collision problems using conservation of momentum. So, what we were saying is that the total momentum before is the same as the total momentum after. And what that means is, if I know that the momentum of this guy, this 2 kilogram guy, I know the change in momentum of this 2 kilogram object, right? Before, what was the momentum of this one? Momentum before of just this object was, it's always mv, right? So it's going to be 2 times 3. It was 6 kilogram meters per second. And afterwards, noting the sign convention, now it's going to the left. So it's going to be 2 times negative 2, which is minus 4 kilogram meters per second. Now, if I'm just looking at the change in momentum of that first object, remember, change is always final minus initial. So the change in momentum of this object is final minus initial is minus 10 kilogram per meters per second. And because of conservation of momentum, if this one here lost 10 kilogram meters per second, well, it's got to be conserved somewhere. And that means it all went to the second object. This guy's loss was this guy's gain. So actually all we needed to do was calculate the change in momentum of object 1, and then we can automatically know, due to conservation of momentum, that that's actually the same as object 2. However, I wanted to show you guys the collision thing, and anyway you get the same answer. So there you go. Now you have two ways and you're that much more flexible. This question says a block placed on a horizontal surface is pushed by a force F equals 12.0 newtons from point A to point B as shown in the figure. So in the figure, I mean, they're showing it to you like midway, but okay. If M equals 2 kilograms and D, the distance here between A and B, is 15 meters and theta, the angle of the incline, is 30 degrees, what is the amount of work done by the force? So work done is the force times the distance parallel to this force. And I stress this, that they have to be in the same direction. For example, in this case, look at the D, the distance or displacement. It's going horizontally to the right. But look at the force. The force is not horizontal. The force is slanted this way. So what I'm going to need to do first is figure out this horizontal component of the force. How about we call it F of x or F sub x? And that multiplied by this distance will work. So here's the shortcut. What you do is you do work equals F times D cosine theta. What that's going to do is going to give you that parallel component that's parallel to D, so that you can have them in the same direction. So in our case here, we can just put in these numbers, which are 12 newtons, and it moved for 15 meters. And you have to multiply that by cosine 30, because what that's doing is giving you this F of x component. Okay, if you put these in your calculator, you're going to get 155.88, etc. joules, which will round off to 156 joules, which would mean this one is the correct answer. So I just want to reiterate this. If you have a force and a distance which are not parallel to each other, they're not acting in the same direction, well then you can't calculate the work. You can't do 12 times 15. I know this one, the answer is 12 times 15. This one is incorrect, because you really need to take the component which is parallel to D. Okay. The second thing I want to tell you is, if you're looking at this equation for work, F times the distance, I can be, for example, standing in front of a wall, and if I'm angry at the wall for some reason or another, and I'm pushing the wall, and I'm pushing with all my might, and I'm pushing with like 100 newtons, but the wall does not budge. Do you know how much work was done? 0. Because if there's no movement, if there's no distance traveled, then the work will be 0. Okay, and that's important. That means there's no, and I haven't transferred any energy into this wall if it hasn't moved. Okay, work done, by the way, in physics, a very, very good rule of thumb, when we say work done, this is almost always replaceable by energy transferred. Energy transferred. That's something I found really, really helpful when I was learning this. Okay, on to the next one. A 50-gram block is attached to a horizontal spring with spring constant K equals 3,600 Newton per meter. The spring is compressed by 5 centimeters. There you go. It's being squished, basically, as shown in the figure. When the spring is released, will the block be able to cross the top of the hill with height 10 meters? So, as you can imagine, after you let go of the spring, there's a lot of potential energy here. It's going to fling through this way. And the question is, will it have enough energy to actually make it over? So this is a question of energy and conservation of energy. Now, first let's start with the spring. As you can imagine, when you squish a spring, the spring is trying to go back to its equilibrium point. It's trying to go back to how it was in the beginning, right? You can probably picture, if you squeeze a spring, it wants to push back. And in fact, if you pull a spring, it wants to pull back. It's the same idea. In this case, let's call it elastic potential energy. Okay, the elastic potential energy of a spring is calculated as this: 1/2 the spring constant times the extension squared. And by extension, I don't mean length, I mean how much you've compressed it or stretched it. Okay, in our case, we know these values. So the potential energy in here is 1/2 3,600, which is the spring constant, times 0.05 squared. Now the spring constant, by the way, every spring has its own constant. It depends on the material you've used, on the thickness of the wire, on how many coils you have, etc. Every spring has a certain amount of force it takes to move it by 1 meter. And if you put that in your calculator, you'll get 4.5 joules. So this block right now will have 4.5 joules worth of elastic potential energy from this spring. Now, a very important law of thermodynamics is that energy can never be created nor destroyed. It can only be transferred or transformed. That means it can only go from one object to another, or it can go from one energy store to another, like elastic potential energy, to kinetic energy, which is the energy you have when you are in motion, or to gravitational potential energy, which is the energy an object has due to its position in a field. So think about something that has height. Something which has a height, let's say a ball on top of a table or something, it has a lot of gravitational potential energy. This energy, for example, if I drop this ball, it would really start to move downwards with more and more speed, wouldn't it? Because gravitational potential energy can be transferred to kinetic energy. In fact, remember when we talked about work done, I had to do some work to get this ball up here, right? Imagine this is a very heavy ball and I had to do some work to lift it up. Work done is energy transferred. When you do work to lift this object up, it now contains energy, gravitational potential energy. In our case here, let's see how much gravitational potential energy would it be to go from this position over here to 10 meters higher, as the question says. So we're going to substitute some of these values. Instead of using grams as they have, I'm going to divide it by 1,000 and get kilograms. We're going to use 9.81, which is the gravitational constant, and we're going to multiply by a height of 10. So a change of height in 10, and if you put these numbers in, you will get that you need 4.9 joules of gravitational potential energy between this level and that level. So if I only got 4.5 from this spring, and now imagine there was no losses on the way here, which realistically there would be some friction here as this block slid across this. We don't even know how long this is, right? So imagine there was no losses and it had to get all the way up. It just wouldn't have enough energy, right? Energy is not going to come from nowhere. The energy it needs to get up had to come from the spring, from the push of the spring, and it's simply not enough. So in this case, I'm afraid the block it won't bounce back before reaching the top. It'll slide back. I think that's what they mean. It'll go all the way up and then it'll slide back down. So the answer is D. This question was about the conservation of energy, and that's how you do it. Okay, ladies and gents, this question is kind of a step up. They kind of escalated quickly, but here we go. The only force acting on a 1.8 kilogram box moving along the x-axis is given by f of x equals 4 times x Newton, where x is in meters. What's the total kinetic energy of the box from x equals 1 meter to x equals 5 meters? So here's the box. Let's say we're over here. This is x is 1 meter. So it's a positional thing. And this is x is equal to 5 meters. And you have this box over here. And this box is being pushed. But this force is not constant. This force is a function of its position. That means when you're over here, the force will be 4 times 1. The force here will be 4 newtons. But by the time you're at position 2, 2 meters, this is going to be 4 times 2 meters, and the force is going to be 8. And by the time you're at 3, it'll be 12, etc. So the force here is variable. That's what this means. The force is a function of the position here. Now, in this case, we have to use integration. We know that usually work done is the force times the parallel distance. But in this case, because the force is varying with the position, we're going to have to use integration. We're going to say the work is the integral of f dx, which is a function of x, from, let's say, x1 to x2, the initial to the final. Okay? In your booklet, you'll see that this is f ds. S as in displacement or position in this case. It's the same idea, okay? I'm just using x because in this question they literally put x, okay? So we're going to do this integration and we're going to get the work done. Now, why am I getting work done? The question says, what's the total kinetic energy? Remember what I told you. Work done is energy transferred. So whatever work was done on this box is actually the amount of kinetic energy that will be transferred to the box. So these will be the same, and this is how you find it. Now let's plug some numbers in here. So the initial position was 1 and the final position is 5. The force they've told me, the function in x of the force it's like a function, right? Like math, it's f is equal to 4x. So hopefully you've done your calculus. If not, then please do check out the calculus videos that we have. They're very helpful. The integral of 4x is simply going to be 2x squared from 1 to 5. And the way you evaluate this is you put 5 in here first. You put the upper limit. So this is 2 times 5 squared minus 2 times 1 squared. This means 25 times 2, that's 50, minus 2, and that's going to give you your answer of 48 joules. And that would be answer number 1. So this question was about a variable force, so finding the work done or the kinetic energy transferred. When you have a variable force, they give you a function of the force. So the force is no longer like 4 newtons or 10 newtons. It actually changes. It's a variable force. It depends on where you are. And in this case, in order to calculate it accurately, you can't just take it at different intervals. You have to integrate from the beginning position to the final position. Okay, so hopefully those ones have helped. I'm going to come back with another video for physics. Again, giving you any tips and tricks that you need to do absolutely great on this exam. I'll see you in the next one.